extra, so I'll start now. I'm the interim chair of the CS department now, so don't know my name because I don't know. And so first of all, if we see there's a lot of, this is going to be a very exciting, I can assure you, a very exciting talk. But the size of the audience doesn't indicate it. Perhaps I should send you an email. My representative, my rule is now that I go to places that somebody I know who is epidemiology goes to. And I can assure you that I know that somebody epidemiologist is coming here. So don't worry about it. But I assume that some of it has probably to do already with some daunting crowded places, but some countries in Europe, they have now a law, no more than 5K people together, but we are very far. So today Sriram is our faculty member, and because he has not only because it was exciting news, but because I thought that we have a lot of faculty from other places passing by, and why the shoemaker will have shoes. We don't know about our own faculty, we know about the faculty we take courses from, but we don't know from other faculty. So I will now try to get some of the faculties that I'm not sure. Why don't you do a CS? Oh, I don't want to. It's like I'm pushing myself. No, nobody is pushing. I'm pushing. Okay, so there is an excuse. You can. I hope it's one in a sequence of not only you, but faculty will come and we learn about each other. And today we have Sriram, and I'm not good with last name, Indian last names, so I have a friend that told me how to remember. Say, remember in Spanish, 5, Sanka, and they say, Sriram. Now we know, I remember forever. So we have Sriram, and I will learn about what he does. I know what he does, probably less than you, because I didn't take about a course about TensorFlow and stuff like this. So I will let somebody who knows more, Professor Elazar Askin, to present to you Sriram in terms of his technical regulation and abilities.
Great. So it's a great pleasure to introduce Sriram, who's going to be talking about some new work. This work actually really was hit the news about 2 weeks ago. All over the world, there are articles about it. In fact, many of the people heard him on NPR on their way to work, which is very rare for you can find his interview online. Let me say, so Sriram came to us from Harvard, where he was a postdoc, and during that time, he was one of the first faculty that was working on, first researchers, to look at the contribution of Neanderthal genome into human DNA, and his group discovered that about 1 to 3% of Europeans' DNA originated from mixtures of Neanderthals. And since that time, he's been at UCLA. He's been spending half of his time in machine learning and half of his time in bioinformatics, and a lot of the bioinformatics has been looking also at other questions in ancient DNA. Since Sriram has been here, he's won many awards. This includes the Alfred P. Sloan Fellowship, the Microsoft Fellowship. He also won the engineering-wide Best Teaching Award as well. So he teaches a lot of the material that he's going to talk about in his classes, in his graduate class, that he teaches every fall. And so this is actually what he's going to be talking about today is a kind of major new finding that he discovered in ancient DNA.
So, thank you for those introductions, Elisa. Can you hear me at the back? Okay, so today I will spend some time talking about this recent work that my group has been pushing for the last couple of years, but also giving you a little bit of context of what this finding implies, what is the implications for understanding biology, evolution, and what are some of the computational questions, statistical questions it leads us to. So, as a background, a lot of what we work on is in understanding genomic data. So the genomes, again, feel free to interrupt me if you have questions, if you have terms that are unclear, happy to answer them as we talk. So the genome, so this is this entity that all of us carry, that we inherit from our parents. 3 billion long sequence, A, C's, G's, and T's. And what I'm interested in is in methods that allow us to interpret and understand our genomes. So this is a complicated question, and the reason why we as neuroscientists are in a position to be able to answer this question and contribute to this is because of the availability of data from genome sequences. So the kinds of questions we're interested in is how do we take genome sequences and understand mutations or changes in our genome that are associated with diseases, which of these mutations are responsible for certain clinical traits. We're also interested in doing this at scale. So as we speak today, we now have data sets of genome sequences from hundreds of thousands of individuals, and that raises lots of interesting computational challenges. In addition to the relevance of the genomic sequence to understanding disease associations, there's another reason why I'm interested in the genome, and that is the fact that by looking at these mutations, we can say something about human evolution. So what I'm going to be focusing on today is this other aspect, which is by looking at genome sequence data, we'd like to reconstruct human origins and human history. And it turns out that this kind of an understanding also has relevance to our understanding of disease biology. So to give you a little bit of a background about this field, it's been about 20 years since the human genome sequence, first human genome sequence. And today we have lots of genome sequences from hundreds or now thousands of individuals. And by looking at these genome sequences, we are building a picture of how human populations are related. So the broad outline of this picture is that present-day humans, so that's all of us, we originated in Africa around 200,000 years ago. And then there was this migration out of Africa. And this migration was the founding of the populations outside of Africa. So there's the small set of individuals that left Africa, and these populations went in different paths and gave rise to the present day individuals outside. K is thousands of years ago, so hundreds of thousands of years ago. So that's kind of the broad picture. But now there are wrinkles in this broad story. So if you talk to people who are studying human evolution, anthropologists, archaeologists, what they say is what is surprising about this spread is that around this time, humans, modern humans, were not the only human-like creature. So there were other populations, we call them archaic humans, who were also existing. This is based on fossil record. And the most well-known of this are this population called the Neanderthals. So the Neanderthals, they appear in the fossil record around 300,000 years ago, and they vanish around 30,000 years ago. And there is clear kind of overlap in space and time between when modern humans existed and when Neanderthals existed. And again, for those of you who haven't seen, these fossils are skulls. This is a modern human skull. This is a Neanderthal skull. And there are all of these questions in evolution about why one population, the Neanderthals, went extinct. Why did modern humans become so successful? What are the biological differences, if any? For example, there are conjectures that modern humans were successful because of language, because of abstract thinking that allowed them to organize or self-organize. And so, all of these are interesting theories. And the reason why now we can begin to answer them is now we have data. So we have now genome sequences from not just modern humans, but these archaic humans like the Neanderthals. So this begins in 2010 when the first genome sequence from a Neanderthal was made available. So this was a cave in Croatia from which this genome sequence was obtained. Actually, it was 3 of these bones in the thigh. Each of this gave a little bit of DNA, and that allowed us to assemble the first Neanderthal genome sequence. It was a technical achievement. Turns out, when you have a bone that lies in the ground for hundreds of thousands of years, there are all kinds of chemical changes that happen to the DNA. It gets broken down into really short fragments, often just hundreds of characters long. Most of the DNA is actually bacterial at some point. The bacteria invade the bone, and so you no longer have a lot of human DNA. Finally, you have contamination from other humans. So people who have touched the bone, they handle it, and so each of this presents technical challenges. And so all of this had to be overcome to actually get access to the first such archaic human. Yeah.
We have Neanderthals skulls, presumably skeletons. Why would we need to rely on these little fragments for the DNA? Why wasn't it awesome from all these skulls and everything else?
Yeah, so the answer to that is twofold. One is it's never clear which of these fragments actually retains DNA. So a fragment that, like the skull, that looks like it's big, doesn't necessarily have a lot of DNA embedded in it. So there's a huge trial and error process, and what actually happens is people screen thousands of these bones to find one which has enough DNA that we can work. The second is archaeologists are very reluctant to part with skulls. They want to analyze them and make inferences on them. These are things which are not informative for them. So they are happy to have genesis to analyze. Alright, so this presented an opportunity where we can now analyze these genome sequences. And one of the first questions, and this was a big debate in human evolution, was whether there was some kind of mixing between these populations, or whether this was just a process where modern humans come in, they completely replace the Neanderthals, and they spread to parts of the planet. So to do this, there are many ways you can try to look at it, but one way was you take this Neanderthal genome and you compare it to different other modern human genomes. In this case, you're comparing a Neanderthal genome to an African and a non-African genome, and you can compute a distance measure. And what we find is consistently, the Neanderthal genome is always a little bit closer to any non-African genome compared to an African genome. So why is that? Turns out there are multiple possible reasons for this. And one reason was there was mixing between the ancestors of non-Africans with Neanderthals after non-Africans left. So in this picture, there was this small group that left Africa, and they mixed with Neanderthals, and that's why all of them are consistently close. Turns out, we can actually say something more. We can actually date when this mixing event happened. And for this, we use a property of how our genomes are transferred. So this is a property where when a person transmits their genome to their offspring, you actually end up transmitting a shuffled copy of your genome due to this process called recombination. So the copy that you end up transmitting is a mix of the copy that you've inherited from dad and mom. And this process happens at a certain rate every generation. And so what happens is that leads to certain patterns that you can exploit to date these extremes. So here's an example of how we would do this. So you have the genome of a modern human, the genome of an archaic human, in this case a Neanderthal. And if you look at the first generation of this mixture, you'll have an individual like this who has one copy of the genome from the archaic, the other copy of the genome from the modern. Now in the next generation, you start seeing recombination come into play, where this individual has the prefix of their genome from the archaic and the suffix from the modern. And that's because there was a recombination that stitched up the archaic and the modern sequences together. And this is a random process, but it happens at a certain rate every generation. And so if you look at a person today, they're going to have parts of their genome that are modern and parts that are archaic, and the lengths of these segments are going to be indicative of when this mixing happened. So if mixing happened just a few generations back, you'll have these large segments. If it happened in the distant past, it's going to have these small segments. So now we can use this to actually figure out or back out the date of this mixing event. And this is a plot. I'm not getting into the statistical details, but if you have a measure of this length of the archaic segments versus distance along the genome, it has a certain decay, and we can use this decay to actually estimate this. And we get a date of interbreeding between these populations of around 50,000 years. So modern humans left Africa around 100,000 years, and around 50,000 years ago was when this mixing event happened. We can also estimate how much of our ancestry comes from this mixing, and we estimate around 2% based on, again, these kind of statistics. Alright, so this is all about the global proportion of Neanderthal DNA. But one question that everybody was interested in is, could this have had some impact on biology? So it turns out that Neanderthal DNA is quite different from modern human DNA. It has mutations that are never seen in modern humans today. So is it possible that all of these mutations that came in because of this Neanderthal gene flow event could thus have had some impact on human health? So we were interested in this, and we were part of the study, which was one of the first to look at specific regions of Neanderthal DNA. So this was a study that was done in Mexican Americans. It was trying to associate genetic mutations with risk for type 2 diabetes. And we ended up discovering a novel risk variant for type 2 diabetes in Mexican American populations. When you look at this risk variant, it has this interesting distribution where the risk variant is essentially absent in Africa, and it's present outside of Africa, and it's at relatively high frequency in the Americas. That's why we discovered it in Mexican Americans. And then we compare the risk variant that we discovered to the Neanderthal genome, and we find that there's nearly an exact match. So this was one of the first examples of a variant that affects the risk for a disease that could be tied to this kind of an admixture. Since then, there were several other notable examples.
So how does that show up in on the African continent? I mean, is it a mark of recent colonial admixture?
How does this mutation show up in Africa?
So is that tied, if it's tied to Neanderthal populations, then how does it show up in Africa?
It does not show up in Africa. So what we are seeing here is, so this pie chart is telling you there are two possible variants here. There is the variant that is low risk for type 2 diabetes and the high risk variant. And what we are showing here is what is the proportion of the high risk variant. So in Africa it's essentially at 0%, whereas outside of Africa is where we start seeing this variant. And when you go to the Americas, it's at even higher frequency. And this is exactly the pattern that you would expect if this were introduced into modern humans via interbreeding. Okay, so since then there were many other examples which try to figure out add a given gene that I care about. Say there's some gene that is interesting. Is there evidence for this gene coming in through Neanderthal interplay? And there were several such examples. Many of them are actually genes that are important for immunity-related function. And there's this interesting hypothesis about why immunity-related genes might have a lot of Neanderthal DNA. But then, given these examples, one of the questions we were interested in is, can we do this in a more systematic manner? Instead of looking at one gene at a time, can we look across the person's genome and ask, is there Neanderthal DNA at a given position along the person's genome? So this led us to build what we call maps of Neanderthal DNA. And essentially what we mean is, can we go to a person's genome and color them according to where they have Neanderthal DNA. So we don't know these colors, and that's what we'd like to back up given genome sequences from the individual. So the basic idea is straightforward. So we have a test genome, and we have an archaic genome, in this case the Neanderthal genome. And we also have genomes from African populations which we know don't have Neanderthal DNA. And our goal is to go along this test genome and color it according to where it might have come from. So in this case, it's a pattern matching problem. In this case, we would say that this portion of a person's genome is closer to the archaic, and so it likely comes from the archaic. So the way we did this is we actually wrote down a statistical model for inferring Neanderthal ancestry. The idea is this is fundamentally a sequence labeling problem. So we're going along a person's sequence and labeling the ancestry. And there are a couple of things we'd like to incorporate into this model. So the first thing is this fact that recombination hands down parts of your genome together. So what that means is, if I tell you you have Neanderthal DNA at position 1, that makes it pretty likely that you have Neanderthal DNA also at the adjacent position, simply because of the property by which your genomes are transferred. So we like to build a model which takes into account this correlation structure and tells you where you have Neanderthal DNA. So the model uses data that looks like this. So you have, say, the European genome, and we have the Neanderthal, and we have African genomes. As I said, Africans are assumed not to have Neanderthal DNA. And we'd like to label this person's genome according to whether they have Neanderthal or modern ancestry. So we are building a probabilistic model of this vector of zeros and ones. We call this the local ancestry vector, given all of this data. There are some technical challenges, and I won't say too much about it. One technical challenge is, if you actually try to model this vector, it turns out to be what we call a non-Markovian process, which means the probability of seeing Neanderthal DNA at position 2 depends on what you saw at position 1. The probability at position 3 depends on 1 and 2. At position 4 depends on 1, 2, and 3. And so you have this dependency that is extremely hard to capture. So the way we do this is we borrowed ideas from NLP and speech processing, where these kinds of models, called conditional random fields, have been very successful at modeling these non-Markov or long-range dependencies. I won't say too much about the technical details, but essentially we are trying to predict the joint probability of the ancestry vector. So Z1 through Z4 are the ancestry vectors, and so we are trying to model the probability of this ancestry vector given all of the data that we observe. And the way we do this, one way to do this, is we write down certain functions or statistics that couple each of these ancestry labels to the data, and then we have functions that couple the ancestry labels at adjacent positions to each other. And this model has certain parameters, and so we have to optimize over these parameters to get good. So to give you an example of the kinds of features that we go into this model, here is one example. So this is a feature that looks at one position, at the mutation patterns at that position. So here we have a mutation in the non-African that is also present in the Neanderthal, and this mutation is completely absent in the African. This is exactly the pattern that we also saw in the type 2 diabetes example. So this by itself is very weak evidence, On the other hand, if you now saw many of these mutations next to each other, then you accumulate additional evidence that this is actually Neanderthal DNA. So we built this model, we trained the parameters, and the result is we can now compute maps of Neanderthals. So here is an example where you apply it to individuals from the 1000 Genomes Project, a big database of publicly available genome sequences. So this is a European individual's genome, Chinese individual's genome, and an African individual's genome. And what you see is clearly there are many places where the model is confident of Neanderthal DNA in the non-African genomes, and relatively few such positions in the African. We did some additional validation, so we did simulations to get a handle on the false discovery rate and the sensitivity of this model. Typically at a false discovery rate of about 10%, we recovered anywhere between 60 to 80% of the Neanderthal. We then applied it to all of the genomes in this 1000 Genomes Project, and effectively we see that we recover substantial amounts of Neanderthal DNA in Europeans and East Asians, relatively little in African populations. So after this, we looked at other data sets. So people have been getting genome sequences from across the world. So this was a data set of about 200 genomes from about 100 different populations across the world. And we could compute the distribution of Neanderthal DNA across all of these individuals. And what we see based on these methods is, again, substantial Neanderthal DNA outside of Africa, but we also see variation across different populations. And now there's a lot of hypotheses that is trying to explain this variation. Could it be the case that there were multiple such Neanderthal intermixing events that were population specific that could have led to this variation? So that's an ongoing research question in human evolution.
How can you tell the difference between multiple admixtures and a single given the data that you have?
So you're looking at the total proportion of Neanderthal DNA, and the assumption is, on average, this Neanderthal DNA is going to be fluctuating randomly across populations. So if there was a single event and the population split, then averaged across their genome, it should be close to statistical variation. On the other hand, if you see large differences, then you need some other explanation. So one explanation is there was other interbreeding events. There could be other explanations like selection and more complicated possibilities as well.
So, how do you validate? You said a little bit of validation, but you obviously don't have like labeled examples of like, you don't really know the ground truth, right? So the validation is in terms of getting things that line up with what we know about where populations were.
Yeah, so there are two sources of validation, so that's exactly right. All of this is largely unsupervised, so we don't know the true labeled places of the genome where we have Neanderthal DNA. So a lot of this is trying to see how much of these predictions line up with what we know based on other methods. For example, the fact that you should see a certain trend across different populations, or certain genes we expect should pop up. The other thing which we also do, which I haven't gone into, is for all of these we have other ways of statistical testing which are not as precise, but we can show mathematically are unbiased. And often we verify these predictions with these unbiased but less powerful statistical estimates. But yeah, in general, all of these have to be verified using complementary lines of evidence. Alright, so this was all about Neanderthal DNA. Around this time, or actually several years back, there was another major finding in this field. So this is a cave in Siberia. It's in a place called Denisova Cave. And this was around 2011, where archaeologists found this pinky finger. That's what you have here. And again, they decided to test it for DNA. So there was initial hypotheses about what could this be. Possibly this could be human, this could be Neanderthal. Those were the two obvious candidates. But it turned out it was neither human, modern human, nor Neanderthal. So it was this new population called the Denisovans. So the Denisovans are this population which is actually a sister group of the Neanderthal. So if you build a tree, you have a split between modern humans and and this branch. This branch then splits into the Denisovans and Neanderthals. So this arrow here is this interbreeding between Neanderthals and non-African ancestors. Now again we can ask the question, this new population, how does it relate to other modern human groups? Turns out, again there has been interbreeding between Denisovans and other modern human populations, specifically populations lying in Oceania. So this is populations that lie in islands of Australia, are populations which have 3 to 6% of Denisovan DNA. So these populations both have Neanderthal and they have Denisovan DNA. And it's quite interesting because this was one of the first discoveries that came entirely from genetics. So previously Neanderthals, we had fossil record, we could say this is what we expect. This was particularly surprising because this was entirely made based on the pinky finger. There was no evidence that this was unusual, and genetics was saying that this was something quite. We can extend these kinds of methods to the study of Denisovan DNA in human populations, and here again we see that we find substantial Denisovan DNA. These are the populations in Oceania and Australia who have substantial Denisovan DNA. Turns out there are also populations in East Asia, particularly Tibetan populations, have quite a bit of Denisovan DNA. So everything I've talked about is now building these maps. We can do more than just look at how much of the person's genome has Neanderthal or Denisovan DNA. So now that we have a map, we can actually ask, along a person's genome, how is this DNA distributed? So this leads us to looking at fine-scale maps of archaic DNA. So here, what I've done is we've arranged the 22 chromosomes and the sex chromosome in a circle, and we're going along every position, and we're counting up at a given position how many people in this database have Neanderthal or Denisovan DNA. So if you see a line, that's telling you that's a place where large numbers of individuals carry Neanderthal or Denisovan. So now by looking at this map, one of the things that was interesting is there's a fairly non-random distribution of this archaic DNA. So we built models and we asked what would it look like if this was just randomly distributed, and then in some places it went low, in some places it went high. Turns out this is not the pattern that we expect. So there are some places in the genome which we call peaks of archaic DNA. So places where many individuals today carry the archaic mutation as opposed to the modern human mutation. So here's one example, it's an extreme example. So this is a gene which has been known to be involved in skin color and pigmentation. And this is a gene where more than half of Europeans today carry the Neanderthal version. So around 50,000 years ago, there were 2% Neanderthals, so 2% of the population would have carried this gene. Today it's more than half. Again, we can ask, is this random or is this expected? And it turns out a process by which the gene is moving up or down in frequency randomly, so we call that neutral inhibition, cannot explain this observation. And so what we are convinced is this is a gene where it has risen up in frequency because of some positive impact. So we think that this must have been adaptive for the molecule. So here's another example. So this is a gene called EPAS1. So this is a gene where the mutations are known to be extremely important for tolerating to low oxygen environments. So this is a gene where there's a mutation that is found to be at very high frequency in populations that live at high altitude environments like the Tibetans. And if you examine what this mutation is that confers high altitude adaptation, turns out that this is a mutation that was inherited from the Denisovan. So what we find is there are peaks of these archaic DNA, and at least some of them have a clear measurable effect on ability of human populations to survive in different environments. On the other hand, there are other places in the genome which are devoid of archaic DNA. We call them deserts of archaic ancestry. So here there are places where, as far as we can tell, no modern human individual carries the archaic version of the gene. Some of them, again, have an interesting underlying biology. So here is an example where this is a position on chromosome 7, which is a desert for archaic DNA, both Neanderthal and Denisovan DNA. And it turns out it's about 10 megabases long, so it's a pretty large chunk of the genome. And this is a desert that overlaps a gene called FOXP2. And the reason why this is interesting is this FOXP2 gene is known to be an important gene for speech and language. So the hypothesis is, this is a hypothesis, is that these are places where there is a human mutation and there is the archaic mutation. And the archaic mutation is less fit, or less deleterious compared to the human mutation. And that is the reason why the archaic mutation was removed quickly after it came into the human gene. That's just a hypothesis, and there are several groups that are actually actively testing this. And this is another quantitative way of seeing this. So we asked whether, if you look across a person's genome, is it the case that archaic DNA, is it adaptive, is it deleterious? And so what we did is, we looked at how much archaic DNA is present in a person's genome across different parts of the genome, built by what we call selective constraint. Selective constraint means here are places in the genome which are highly selective, highly functionally constrained, known to be important based on biology. Here are places in the genome which have low constraint. Based on biology, we think they're not necessarily important. And what we find is both the Neanderthal and the Denisovan DNA tends to get lower as you go to regions which are under stronger constraint. So the picture that's coming from looking at these maps is, on the whole, the archaic DNA was deleterious, not necessarily good for us, and that is why it has been removed in parts of the genome which are selectively important. But that's not the full story. There are other places in the genome where it has actually risen up in frequency, and that's possibly because these were adaptively damaged. So where we are right now is, now we are building maps. We have these statistical methods that are pulling out these regions of archaic DNA, and a major challenge now is to try to see what biological impact this is having. Alright, so everything we have said so far, everything we have discussed is about these populations outside of Africa. The real reason that we've only focused on these populations outside of Africa is because of the fact that we have these archaic genomes to begin with. So the fact that we had this Neanderthal genome and this Denisovan genome allowed us to ask questions about out of Africa populations. So now the question is, what about populations within Africa? Turns out we don't know much. There's a lot of evidence from the fossil record in Africa that there were archaic populations in Africa as well. However, we haven't been very successful in getting ancient DNA out of these fossils. So, largely due to environmental conditions, it's really challenging to get ancient DNA within Africa. So while we now know quite a bit about archaic DNA outside of Africa, within Africa, knowledge is very limited. So this was what we decided to look at. So the goal is, can we say something about archaic ancestry, archaic DNA within Africa, even if we don't have these archaic genomes to begin with? So again, the challenge here is we don't have label data. So every time we have a method, we have to worry carefully about the biases inherent in this method. So to try to get at this question, we actually have two complementary approaches. We'll talk a little bit about both of them. So the first approach uses some theory from mathematical population genetics. So this is the study of how populations evolve and what we expect to see in genome sequences if populations are evolving in a certain manner. And so the first line of evidence is going to come from the field of mathematical population genetics. And the second one is something where we are going back to our statistical approaches And we're going to devise a method that can pull out these segments of archaic DNA, but do so without needing an archaic gene. So we're going to develop a reference-free method for building these maps of integration. So let's start with the first one. So we're going to start with this mathematical object. It's called the site frequency spectrum. So the site frequency spectrum basically is looking at the genomes of a bunch of individuals and building a histogram based on how frequently a mutation occurs. So the idea is simple. If you have genome sequences, let's say from Africa in this setting, every line here is an individual, every column here is a position. We go along each position and we're going to ask how frequent is a mutation at that position. So in this setting, you might have a mutation occurring in 3 out of 5 individuals. Another mutation might occur in all individuals. So now we can calculate it and we can build a histogram of the number of mutations that occur at a certain frequency. Turns out, this summary of the data, called the site frequency spectrum, is extremely informative about how this population evolved. For example, if this population just evolved by itself, the site frequency spectrum has a certain pattern to it. On the other hand, if there was introgression into this population, it has another pattern to it. So potentially, we might be able to use this histogram to say something about how these populations have evolved. The challenge is, the site frequency by itself has too much information. So it not only is determined by the history of this population, it is also determined by other processes that we have less information. For example, mutation rates, selection, and so on. So we want to have a summary of the data, which is informative about introgression and is robust to everything that we don't care. So to do this, we came up with a different summary, which we call it the conditional site frequency spectrum. So what this summary of the data is doing is it's only looking at positions where when we compare the Neanderthal genome to the chimpanzee genome, which is the genome of the ancestor, the Neanderthal and the chimpanzee genome are different in what ways they can. So now we're going to build a histogram exclusively based on those positions where the Neanderthal and the chimpanzee genome differ. This we call the conditional site frequency. Now, why is this an interesting summary of the data? So this relies on some population genetic theory. So let's say the true history of our population was something like this. You had an ancestral population. At some point it split into two. One was the ancestors of the Africans, the other was the ancestors of the Neanderthals. Now if you compute this conditional site frequency spectrum, we expect it to look uniformly distributed. The reason for this, and we can show mathematically why that's the case. So it turns out, the mathematical reason for this is at the ancestral population. So this again has a lot of population genetic theory for why that's the case. This site frequency spectrum, which tells you what fraction of your mutations have a certain frequency x, it has a form that looks like 1 over x. In other words, the site frequency spectrum says if you have a mutation that's going to be present in one individual, that will be present twice as frequently as a mutation that's present in 2 individuals, 3 times as frequently as a mutation in 3 individuals. So this is a well-known model in population genetics. Now we're going to look at the conditional site frequency. So what is the conditional site frequency spectrum? We're only restricting to those mutations where the Neanderthal carries the mutation. So the Neanderthal is what we call derived compared to chimpanzee. So the probability of doing this, if you have a mutation at frequency x and you randomly sample a Neanderthal genome, the probability that this Neanderthal genome carries that mutation is exactly x. So now we are filtering based on all sites according to this probability, and so the result is what we call the conditional site frequency. So at frequency x, you have 1 over x fraction of sites, and the probability of picking a site is x. So the conditional site frequency spectrum is So this is theory. Now what do we see in the data? So in the data, so this is data from an African population, a West African population in the 1000 Genomes Project. So if you now compute the same entity, you get something that's quite far. So there's a mismatch between what theory predicts and what the data shows. So what might explain this? Oh, and before this, we looked at other West African populations, not just the Yoruba, and all of them show this characteristic, U-shaped pattern. Of course, there's possibilities of technical artifacts. So there are errors of all possible kinds, errors in the genome that we're looking at, errors in the archaic genome, errors in how we identify these different mutations. So we asked whether some of these could explain this pattern. Turns out, these errors could explain them, but the rate of these errors is way higher than what we know from other studies. Turns out there are other biological processes that might also explain them, and I won't get into the details. And so to verify this, we did simulations under these models of biological processes. We filtered the data in different ways to try to figure out which parts of the genome are less likely to be affected by some of these processes. And we found that across all of these ways of looking at the data, we could rule out these other experiments. We also looked at other models of human history. So we asked, let's build a complicated model of human history. Others have also built such models. And could this explain the data? So here is the blue curve, which is the data. The orange is what we see based on these models of history that we have. And we see that maybe it fits a little bit here on the left, but it doesn't explain all of this. So we conclude that current models, our current understanding of human history, does not explain the data based on this statistical sample. So what else might explain this? And so this led us to models which are what we call models of structure or introgression in Africa. So here is one model that we show does explain the data. So this is a model where there is this population that's split off prior to the ancestors of modern humans, and then it introgressed or interbred again. We call it a ghost population because this is not a population which we have identified based on any fossil evidence. And what we find is this model, which has a ghost introgressing into the African population, does explain this conditional site frequencies. We also looked at other models of introgression. Maybe this is not really a ghost, maybe it's the Neanderthals coming back together and mixing. Turns out, again, we can reject this, it doesn't fit our data, and we can reject this model at a very stringent p-value. There are other models where there was maybe just within Africa there was a lot of structure, population splitting and merging. Again, those do not explain the data quite as well. And we explored a lot of other models which have structure within Africa. So in this setting, for example, we looked at different models of structure within Africa, and we are computing the p-value. So lower p-value means we reject the model across different kinds of parameter settings, and we find that none of these parameter settings allow us to explain using this model. So, take it together. This analysis of the data suggests that a model where there is a ghost population introgressing into Africa could explain this conditional site frequency spectrum. There was one other question we also asked, which is, can we say whether this was an African-specific signal or was this shared between Africa and other African populations? I won't say too much about this, but our current estimates suggest that some of the signal is actually prior to the split between Africans and out of African populations. We can also get more quantitative about this, so we can ask, when did this population split off? How much of the ancestry came from this population? And at what point of time was this introgression event? So at this point, we fit a model with all of these parameters. And one of the interesting aspects of this is this was a population that split off prior to Neanderthals splitting off from modern humans. fairly old population, and almost 11% of the ancestry of Africans comes from this post-archaic population, compared to the 2% or 3% attributable to Neanderthals and Denisovans. So this had a fairly big impact in terms of how much ancestry comes from this population. So that was one line of evidence. We were not quite sure whether we completely believe this, so we tried to figure out if there was another way to look at this. To do this, we now built a map of intracrest DNA. And the key difference now is we have a method that does not require an archaic genome. Clearly, we don't have an archaic genome to begin with, so that's what we want for this. So the underlying idea behind this reference-free method for archaic DNA is if you have enough modern human individuals. So if you look at collection of modern human genomes, simply by looking at the patterns of variation within those modern human individuals, there is enough information to pull out these intracrest. So what we do is we compute a bunch of statistics on these modern human genomes. These are the features that we use to train a model, like the conditional random forest model that we had previously, and use that to predict the archaic. So some kind of examples of the kind of statistics we use. For example, if you have a target genome, so this is a genome in Africa, and this individual has archaic DNA at this position, then what you expect is a number of mutations will fall on this person's genome that are going to be exclusive to this individual. Because this is archaic, most of these mutations are not going to be seen in other individuals. So seeing a signal like this might increase our odds that this is an archaic signal. Similarly, if you take this target genome in Africa and you compare it to another genome sequence, if this was actually archaic, then the distance to all the other genomes is going to be much bigger than if this actually came from a modern human population. So again, you can build a collection of features and use a statistical model to be able to figure out which of these features are informative for making predictions of archaic. Before applying it to the African setting, we had a positive control here, which is the Neanderthal introgression that we've already identified. So now we apply this method first to the Neanderthal setting, and here we compare the prediction from the reference-free method to the predictions from the reference-based method that we had previously. And by and large, we see concordant predictions. For example, as we look at the probability that this method assigns to whether a segment is archaic or not, now we can ask how likely is that segment to match the Neanderthal genome, which we know is what we expect this segment to come from. And so as the threshold of the probability increases, you're more likely to match the Neanderthal DNA than if you are labeled to be not Neanderthal. Similarly, this was the gene that I identified earlier as having high proportion of Neanderthal DNA, identified using the reference-based method. The reference-free method also identifies this as an intracrest DNA set. Again, a lot of the other features also line up, so this makes us confident that this method actually can pull out intracrest DNA. So then we applied it to Africa. So applying it to the West African population, one of the populations, this would be Luba. We find that at a false discovery rate, in this case of 20%, about 8% of the genome is identified to be archaic according to this method. So this is concordant with some of those other estimates that we got from the conditional side frequency spectrum analysis. So given this intracrest segment, we can now ask, is it really closely related to any of the other genome sequences that we have? For example, maybe this came from some other modern human genome. We misidentified it as archaic. We have genome sequences from other populations that are distantly related to the African population. We can also compare it to the known archaic genomes like the Neanderthals and the Denisovans. And so what you see here is the measure of the distance of these intracrest segments. We're comparing the intracrest segment to the non-intracrest segments according to our method. And we find that for all of these, the segments that we label as archaic are not particularly closely related to any of them. again, this is exactly what you would expect if this was a ghost or an unknown. Alright, so those are the two lines of evidence, and so what that leads us to conclude is present day Africans trace quite a bit of their ancestry to this unknown population. This population split off quite far back in the past. So the kind of bigger picture about what this is telling us about human history is this notion that populations that are split hundreds of thousands of years back come back and mix. And this is a common feature no matter which set of populations we look at. So we knew this was the case with out of Africa populations, but we also know that within Africa this is common. And a week after our paper here, there was another paper that also showed instances of these kinds of ghost archaic populations introgressing into other populations. So the bigger picture is this model of human history, which is incredibly complicated, where you have branches splitting off and then coming back together and mixing. So that leaves us with some questions for the future. So the first is, how pervasive is the signal of archaic DNA, and what were these host populations? So one way to answer this, and that's what we're doing right now, is getting genome sequences from other modern human populations that have not been represented yet. So even within Africa, we've only sampled a small subset of the populations. It's an extremely diverse environment. The second is ancient DNA. So this field has been making huge progress over the last 5 to 10 years. So this is a timeline, and this shows the different ancient DNA sequences that have been generated across the world. So this is in Europe, this is in different parts of Asia, this is in Africa, and this is at different points in time, going from most recent to furthest back. And what we see now is we're actually building a picture of how different human populations were at different points. The picture in Africa is still fairly sparse, so again, it's unclear how ancient DNA will progress there. But my guess is, in parallel to the advances in populations outside of Africa, we will soon start having ancient DNA from populations within Africa. So once you have those kinds of genome sequences, we might be in a position to be able to identify what those populations might have. The other question, which I briefly touched upon, is what was the impact of this DNA on human health or human biology? So this is where there's a confluence between these kinds of evolutionary studies and studies that have been undertaken with the purpose of studying health and human disease. So these are what we call biobank data sets. An example of this is a study in the UK called the UK Biobank, which has genome sequences from about 500,000 individuals, thousands of traits. And one of the things we are doing is now using these maps that we built to be able to directly test the influence of these mutations in these biobank scale data sets. So for example, you can look at a position like this, which we have identified as a mutation that is inherited from, say, the Neanderthals, and then put it together with disease or other kinds of trait information. And this allows us to understand in a natural context, so without doing experiments in cell lines, which other groups are doing, what might these mutations have done? Why is it that some of these mutations have become as frequent as 50%? The other question, so this is all about biological and evolutionary impact of these kinds of analyses. The other question is trying to understand how we can actually build a better or a more coherent picture of evolution. So what I talked about today is humans, but it turns out that this picture is actually common across different species. So people have looked at primates, people have looked at mice, butterflies, and as you get genome sequences and you try to build the history of these populations, you soon run into a messy looking graph. So this is a computational problem and a challenge. So far, as a field, we've been fairly good at building trees. So given genome sequences, there's a whole field of phylogenetics, which is about inferring trees from these sequences. Turns out it's a challenging problem, but we do have relatively good tools. We know what methods work, how much data is needed for these methods to work, and so on. Once you start looking at these graphs, we are essentially lacking any good theory. So we don't know how do we make inferences. Starting from all of these genomes, how do we actually build these in some systematic manner? What methods work? How much data we need? And just to give you a hint of the kinds of things we are working on. So the kinds of methods that we are working on are based on this notion of invariance. So the idea is, we looked at the African setting and we said there is this statistic, this conditional site frequency spectrum, this strange looking statistic, that has some nice properties. It is flat when there was no infogression, and it has this U-shaped when there is infogression. But we had to think through this really hard to come up with an algorithm. Now the question is, can we have a method that identifies this statistic automatically for us? So given some picture, given some model of human evolution, can we build these statistics in an automated manner? So we call these statistics invariants. The reason they are invariants is it's some function of the data which has a certain value under a given topology of evolution and has a different value when this topology changes. Turns out that these are actually a very powerful technique for studying evolution. Interesting point, some of the first work, so this is not a new idea, there's been some really old work. So some of the first work is actually from James Lake, professor here in UCLA. But again, a lot of that needs to be adapted to the data and the kinds of problems that we are doing. So with that, I'd like to acknowledge everyone. So the student who worked on the African regression, extremely talented student, Arun. And this was, of course, work across many different institutes, across many different disciplines. I'd like to thank all the collaborators and funders.
So you've inferred, if I understand correctly, the existence of this archaic genome, but you can't really infer what it looks like in particular places.
Right, so you infer this archaic genome
That exists.
and because of the fact that now we can pull out segments of this archaic genome from present-day individuals, we can now actually say something about the genetic makeup of this archaic population. What we are less clear about is the connection to some fossils or connection to some geography.
So for example, if someone finds a button and extracts some DNA, would they be able to determine that that's actually individual from this population?
Potentially, yes. So now that we have these segments, we could have a direct test. So we are making a testable prediction here, and you could ask whether a specific archaic genome that has now been discovered matches up with the segments that we pulled out.
The version with a reference, how does that work given that I imagine there's not that much DNA of these ancient populations? Usually you need a lot of these things to even talk about what the genome of Neanderthal is. So how does that work?
Yeah, that's a great question. So we have one genome. Actually, we have more than one, but for our purposes, we have one genome. And so the question is, why do we expect that we're going to have any power? I mean, those power plots are pretty good, right? We have reasonably good power, if you believe the simulations, of pulling out these segments. So the question is that realistic? Or why do we expect to have any reasonable power at all? So it turns out that is a lucky accident, in the sense that the Neanderthal populations were effectively quite small over a long period of time. And what that means is they had very little genetic diversity. So if you take two Neanderthal genomes and you compare them, it's more bottleneck than, say, Ashkenazi Jews. Way more bottleneck. So very little genetic diversity. So the implication of that is even one genome is a pretty good surrogate for the population. So it's a coincidence that we're able to do this. And again, if the population was really big, we would have had a lot less power to make these kinds of decisions. Of course, now it's changing. Now the ancient DNA field has progressed. We've gone from 1 to 10 Neanderthal genomes. So we actually have additional data we can boost our power.
I hope you don't mind a political question. I mean, we don't have any examples of this ghost population, and it's because if it's in West Africa, a lot of the evidence has been destroyed due to, presumably, the slavery activities that occurred. You know, slavers would go and they would, a few people would hide in caves, they'd go raid people, they destroy the caves and all that sort of thing. And have you thought about to what extent your evidence may be missing indefinitely because of that tradition?
Right. So that's certainly a possibility, but I think there are other reasons why, even though we might have material, so Africa does have material in terms of fossils. So even though you might have the bones and the fossils to begin with, there are other technical reasons, because DNA doesn't survive too well in those kinds of conditions, that have been a bigger bottle. So I do know that there are many the experts in ancient DNA who are trying all these bones, but by and large, they've come up with nothing. So there might be that reason, but I think the environmental reason is one that's more immediate. And you could imagine that as the techniques, wet lab techniques get better, those might actually change.
I also had a slightly political question. So, in case of the Neanderthal admixture proportions, is there any difference in the Neanderthal admixture in the so-called ancient North Indian DNA and ancient South Indian DNA? And can that help shed some light on the controversial Proto-Indo-European hypothesis?
Yeah, that's not a controversial question, but yeah, that's a great question in terms of you seeing whether there are differences in these populations. As far as I know, nobody has looked. And this goes back to the fact that now we have all of these ancient DNA sequences coming. Yeah, so the challenge, of course, is when you're looking at ancient DNA, we have to adapt these methods to deal with the fact that ancient DNA is noisier, has more errors, less coverage compared to modern DNA. So that brings with it a whole host of other technical challenges. But if you're able to answer that, then you could start looking at this. As far as I know, nobody